Okay, everyone. So now we move on and start to talk about the red-black tree. So remember, a red-black tree is also a binary search tree. However, it is augmented with other cool features. And as the name suggests, we are using the red and black color to paint each of the node of the tree. And well, after we apply some of the tricks we are going to learn in the future, and then you will see, well, those operations will guarantee that the height of the red black tree will be a O log n. So remember, one of the painful part of the old version or the basic version of the binary search tree is if in the worst case, if the tree always grows on one side, and what will happen is a search, a insertion, or a deletion can be O n, and that is not so cool. So we want to have a binary search tree which is guaranteed to have O log n in most of the operations, and those are the tricks we want to learn in the red black tree. So in the next few lecture videos, and we are going to talk about one. Well, what are the properties of the red black tree? And number two, we are going to do a theoretical proof that the height of the tree will be O log n. And the last part is, well, we are going to describe some of the operations which may change the red black tree and how they should be designed. And let me give a short example. So for example, if we happen if it happens that we want to delete a node of a red black tree, and then after deletion, and well, we know how to delete a node from a binary search tree, but since it is a red black tree, we have to a little bit more massaging of the tree to make sure that it is still a valid red black tree. Okay, so the five important properties of a red black tree. So the number one, every node is either red or black. So that is obvious. That is why we name that a red-black tree. And the number two, well, every leaf, well, parentheses, now pointers is black. So this is confusing. So when we are talking about the leaf, and the leaf should be the lower level of the tree, and those nodes have no children, right? So that is our definition of the leaf. But let me show you the example of the red black tree. So of course it is not really red and black, it is red and gray, because this is the image I got from our textbook. But if you see on the very lowest level, so let me bring up the laser pointer. So for example, if you see this one, and you will see that is actually a now. So it is the right child of the node 20, right? But well, in the red black tree, the rule is for all the leaves. So for all the leaves we have been talking about, they will have two children, and both of them will be nows. So let's come back. So every leaf which are all the now pointers is black. So this means, well, for all the leaves in the red black tree, well, in the red black tree definition, they are all now pointers, and they are all black. Okay? So the next part, if a node is a red and both children have to be black. Okay, so let's see the example again. So let's try to find a red node. So for example, 17 here. So since that is a red node, and it guarantees for both of the direct children, which are 14 and 21. For both of the children, they are guaranteed to be black. Okay, and for example, like 35 is a red node, and then both of the children are black. Okay, and the number four, every path from node to descendant leaf contains the same number of the black nodes. So we don't really have to pick a root. So for example, let me pick 21 for example. Okay, if we pick 21, and then what we want to count is from the current node 21 to any of the possible leaf. we have to visit the same number of the black nodes. So if I take this way, 21, 19, and now, and then I have visited a total of 3 black nodes if we count the 21. So if we want to do another one, 21, 19, 20, and then a now, and then we visit 3 black nodes again. However, there's one additional red node we have visited, right? So from a node 21 to any of the possible leaves, and we will find that we are visiting the same number of the black nodes. Okay, that is defined as the black hat, and we are going to see that very soon. And the last one, the root is always black, so we can see here. So the next part, we want to use the example to verify all the properties, and we kind of have already done that. So all those 5 properties should be true to make a red-black tree valid. So the next part, black height. So that is the number of the black nodes on a path to the leaf. So now we have 2 different definitions of the height. So the number 1, if we just talk about the height of the tree and then we know the definition. And then we also have the black height. So usually we use the black height of a node. So black height of the node is how many black nodes we have to visit from the current node down to a leaf. And based on the property number 4, if as long as we find one possible path and then count the number of the black nodes, and that is the black height. Okay, so the next thing, after having all those properties and the definition of the black height, remember the goal is we want to prove that for a red-black tree, the height will be O log n. That is our goal. So the next question is, what is the minimum black height of a node with the height of h? So think about that. So if we come back to here, so from the 21 down to any of the possible leaf, and we will see the black height. If we count 21, the black height is a 3. Or if we want to exclude the 21, and then the black height will be a 2, right? So what is the height of 21? So the height of the 21, we should take the longest path from 21 down to a leaf, and that is 21, 19, 20, and a nail. So that is 1, 2, 3, 4. If we count the 21, and that is a 4. If we don't want to count the 21, that is a 3. Okay? So let me come back. So the height h node has the black height to be h divided by 2. So that is the black height is greater or equal to the height divided by 2. So what does this mean? So we have to come back to this example again. So the longest distance from a node down to a possible leaf will be something like this. So a black node followed by a red node followed by another black, another red, another black, another red, another black. So that is the longest possible path from the root down to a leaf. So why? Because we cannot have 2 red leaves right next to each other. So we have to come back to the property. So the property says if a node is red and then both children are black, right? So this means if we have a red node and then the next node down by 1 step has to be black. So this will guarantee that if we have a path from any node down to a leaf, at most half of the nodes we visit down the path can be red, and all the remaining of them are black. So in other words, more than half of the nodes we visit from a node down to a leaf are black, right? So this means, well, a height h node has black height to be greater or equal to the height divided by 2. So this is the part we are going to use in the later proof. So the theorem we really want to prove is a red-black tree with n internal nodes has a height to be the h smaller or equal to 2 log n plus 1. So this is theorem we want to prove. So how do we prove that? Well, we have been doing proofs a lot, and probably you know the answer. And the answer is, of course, we have to do induction. Well, remember, if we want to do induction, the very first is we want to find a very small, very basic case, and we can easily prove that it is true, right? So what is the most fundamental, the easiest, the most basic case we can find? Well, that is, of course, when the current node x itself is a leaf. So what we want to prove is, well, if x itself is a leaf, and then we want to claim that a subtree rooted at the node x, well, in this case, x will be a leaf, contains at least 2 BH. So BH is the black height. So 2 of the 2 powers, the black height of the node x, and minus 1 internal nodes. So how do you want to prove that? Well, this will be our next task.